Okay, rate of change of a unit vector in a rotating reference frame. I feel like I say this for every video I've made, but this is very important. Again, we're also going to be using this in pretty much every problem we solve in dynamics. So the result of this is very important. The video is going to be a bit of a doozy because I don't go through many derivations, but I feel like this one's important. So if you're interested, this video is going to be about the derivation. If you're not interested in it, I get it. You can just skip to the end and see the magical result we're going to end up using. But I think it's good to stick through this video and kind of get some intuition on what's going on. So this is our definition for scalar derivative. It's a limit as time goes to zero of the change in the scalar over the change in time. Okay, that's just your standard derivative definition. We can apply this to a vector and say that it's equal to the change in the vector over the change in time. So this represents a vector after some change has occurred after some delta t, and this is our original vector at time t. So here we go. Say we have our vector at time t, and it rotates up, and now it is at t plus delta t. So it's at some little step in time in the future. Our change in that vector is this delta a of t, and that points from where we were and where we are now. So this is our change in our vector. Recall the definition for the magnitude of a vector. The magnitude of a vector is equal to the square root of the dot product of a vector with itself. If we take this and we square both sides, we'll end up with this right here, right? We killed the square root, so now we just have a divided with a is equal to the magnitude squared. Also take note that the magnitude is a function of time. This is going to be like our implicit differentiation stuff we did in the second video, I think. But a is a function of time. So if we take the derivative of both sides of this right here, we'll end up with d dt of the left side equals d dt of the right side. This right here, we're going to apply the product rule. Derivative of the first times the second plus the first times the derivative of the second. Nothing special there, just the product rule. Here we're going to apply our chain rule, so we bring down the two. Erasing my derivative. So we bring down the 2 times the inside, times the derivative of the inside, which is a dot. So 2a dot. Keep in mind that a dot is the time rate of change of the magnitude of the vector. Now, unit vectors are fixed length vectors. Therefore, only their direction can change. Their magnitude remains constant. Their magnitude remains constant at 1. It cannot change. It is a unit vector. So a dot, there is no a dot. It's 0 because the length isn't changing. So this side is 0 for unit vectors. Remember, for dot product, we can swap the order that we multiply or that we take the dot product of, and it's the same thing. So we have 2 of these. So 2 dA dt dotted with a is equal to 0. Recall our dot product rules. A vector dotted with itself is 1. The dot product of 2 orthogonal vectors is 0. Okay, well, what do we have here? We have the dot product of 2 vectors equal to 0. That tells us that dA dt and a are orthogonal for all fixed length vectors. This only applies to fixed length vectors. And we're dealing with unit vectors, so it applies for us. So let's define some unit vectors with respect to our vector we're looking at, a. So say we have a pointing in this direction. We're going to define a hat parallel, this unit vector, to be parallel or going in the same direction as a. We're also going to define a hat perpendicular, and that's what these little symbols mean, by the way. This one is perpendicular and this one is parallel. A hat perpendicular is always going to form a right angle. It's always going to be perpendicular to vector a. With these directions defined, we can write a, our vector a, as its magnitude multiplied by the a hat parallel direction, right? It's just some length and it is going in the a hat parallel directions. Nothing wrong with that. Let's take the derivative of this. What is the derivative of this? Well, it will be dA dt equals, that's the left side, equals the derivative of this. And we're just going to do the product rule like we did above. So derivative of the first, a dot, times the second, plus the first, times the derivative of the second. That's just the product rule. And we have two kind of components on this. We have the first part is our length change, and the second part is our direction change. Okay, here, let me zoom in a little bit here. So if we write out, what happens to our vector, we have our a hat parallel direction, and this was pointing to the right. And after some time, it rotates by some angle delta theta. So now it is here. After some delta t, our a hat parallel has rotated by angle delta theta to here, to this green vector now. Remember what the name of this video is, rate of change of a unit vector in a rotating frame. So that's what we're doing, we're rotating. We're going to do a little bit of trig now. And one last thing I want to mention. This vector from here, where we started to where we ended, this is our change in a hat parallel. So we have delta theta here. That tells us that off of the vertical, this vertical blue line drawn here, this angle here is delta theta over 2. How, Brian? How is that delta theta over 2? Well, I'm glad you asked. I'll tell you. This here is an isosceles triangle, because this length here, this orange length, that's a unit vector. This green one, that's still a unit vector. So those two sides have the same length side. Keep that in mind, isosceles triangle. So let's take this and we're going to blow it up a little bigger down here. Make it a little easier to see. Since this is an isosceles triangle, we can divide this bigger triangle kind of in half. We can divide delta theta in half, and that'll take us to a right angle right here. And cut our delta a hat parallel in half. Okay? So now we have these two right triangles right here. We have one here, and then we have another right triangle right there. Let's just look at the bottom one right now. So we have this right triangle where the right angle's here, and we cut it in half. So the angle here is delta theta over 2. And so let's take the sine of delta theta over 2. So sine of this triangle of delta theta over 2 is opposite over hypotenuse. So the opposite of delta theta over 2 is half of this length of the vector a hat, the change in a hat parallel. So it's this length right here, which is this blue term, which is a scalar, delta a hat parallel over 2. So opposite over hypotenuse, and the hypotenuse is this side right here, which is a hat parallel, which is just equal to 1. Okay, so sine delta theta over 2 is equal to this, the change in the magnitude of a hat parallel over 2. Let me make that clear. This delta a hat parallel term, this is a scalar quantity. This is not saying the change in the length of our vector a hat parallel. This is saying how much our vector has changed with respect to time, right? So it's gone from here to here. This vector is not necessarily a unit vector. So if we multiply the 2 over, we'll get delta a hat parallel is equal to 2 sine delta theta over 2. Brian, what are you doing? I thought we were talking about why this, what this angle is. Yeah, I'm gonna get there, okay? Hang on. So note delta a hat parallel is not a unit vector. That's what I just said. This is not a unit vector. It is a vector representing how much the unit vector has changed. Okay, so now we're going to start looking at that angle I kind of started this whole rant on. So this is come on now. This here is a right triangle. And we said that this is delta theta over 2. This is 90. This is a right angle. And I'm going to call this angle here beta. the sum of the angles in a triangle need to add up to 180 degrees. So that tells us that beta plus 90 plus delta theta over 2 needs to be 180, which is what I've written here. And we can solve for beta as just 90 minus delta theta over 2, right? We just move the 90 over and we move this guy over. Now, if we have this straight line, this up and down line, this blue line, and we're trying to find this angle here, well, we know that this is 90. So this angle, what I called phi, is going to be equal to 90 minus beta. So let's write that out. Phi is equal to 90 minus beta. And we just said beta is 90 minus delta theta over 2. So 90 minus, and then this is beta. So that gives us that phi is equal to delta theta over 2. Okay, we did it. Okay, now we can use the result. So now we have this here. It's the same drawing we've been drawing. I'm just doing it again. So how do we define our vector, this vector right here, this change in our vector? Well, what do? We go in the negative x in the a hat parallel direction, and then we go in the positive gray y in the a hat perpendicular direction. And this is the exact same thing I did in that DCM video. If you watch that, you'll be very familiar with this. But if we take the sine of delta theta over 2, that's equal to opposite over hypotenuse. And if we multiply the hypotenuse over, then we get that x is equal to this. Same thing for y. Cosine of delta theta over 2 is equal to adjacent, which is y, over hypotenuse, which is the same thing, the change in a hat parallel. And if we multiply it over, then we end up with this right here. These are scalar numbers. These are scalars. So if we plug in for what the change for how to represent this vector in the parallel and perpendicular basis we've set up, we are representing this in these bases. We would say that, well, we went negative x in the a parallel direction, and we just said x was this, so we're plugging in negative x in the a hat parallel, and then we went positive y in the a hat perpendicular. Positive y in the a hat perpendicular. Then, well, we know this. We know what the magnitude of that change is because we found it up here. Remember when I went off on my little tangent? It's this. It's equal to 2 delta theta over 2. So when we go and plug that in, we're plugging in for this, which is equal to this, and then we just carry the rest of it through. Same thing here. We're plugging in. This is this, and then the rest just carries through. So all we did was plug in for the magnitude of the change. These come together to form a sine squared delta theta t, and we don't do anything with this. This just carries through. So now we have this guy. This is equal to our vector, our change vector. We can apply some trig identities. Trig identity 1 is 2 sine squared of x over 2 is equal to 1 minus cosine x. You can see here we have 2 sine squared of delta theta over 2. So we can plug in cosine delta theta minus 1. And then here we have sine delta theta over 2, cosine delta theta over 2. And when we plug into this property, we'll end up with sine delta theta. Okay, now let's take a look at what happens when delta t goes to 0. So as delta t goes to 0, this green vector is going to get closer and closer to its original position until it's overlapping it. And you can see as delta t goes to 0, delta theta is going to 0, right? Because we're getting closer and closer to where we began, to our starting time. So as delta t goes to 0, delta theta goes to 0. As delta theta goes to 0, cosine of delta theta approaches 1, right? Because cosine of 0 is 1. As as delta theta goes to 0, sine delta theta is going to approach delta theta due to the small angle approximation. Now, from the definition on the very first page where we were looking at, the definition of the derivative, when we the change in our vector, which we just defined as this, we're going to take as delta t goes to 0. So this is going to end up being 1 minus 1, because we just went through this exercise here saying that it's going to approach 1. So it's going to be 1 minus 1 in the a hat parallel, plus, sine delta theta is going to approach delta theta in the perpendicular direction, and that's going to be divided by our delta t. Now, what did we end up with here? Delta theta over delta t, right? Because this goes to 0, so all we're left with is delta theta. So delta theta, delta t, in the a hat perpendicular direction, this is equal to theta dot. We ended up with an angular velocity here. Theta dot is an angular velocity. It's the rate of change of an angle. Okay, so we end up with this expression here. The rate of change of our rotating vector, our rotating unit vector, this a hat parallel, is equal to theta dot in the perpendicular direction, which we can represent, we'll commonly call an angular velocity omega in the a hat perpendicular direction. Things are getting interesting now. Let's keep applying this. Now let's apply this to a coordinate system that evolves with respect to time. So say we start with this blue basis, and it goes through over time, it's rotating and whatever, and then we end up with this orange basis. Keep in mind this, let me erase them again. Keep in mind this property we defined. So now, say we, it's the exact same thing we did before here, okay? This is the picture we're familiar with. Now we're just applying it to a rotation about the 3 axis, right? So we have E1, E2, and E3 out of the page. That's where we started. And say we rotated by some delta theta about E3, and so now our basis is here. Okay? Well, again, we just defined this, so we can write d E1 over dt, where E1, this looks a lot like our a hat parallel, doesn't it? Well, it is, right? Is equal to omega 3, so our rate of change in the, about what we're rotating about in the E3 direction, we're rotating about E3, so our angular velocity multiplied by a hat perpendicular. This, E2, is our a hat perpendicular. Doesn't that look like our a hat perpendicular we defined right here? Because it is. Okay? So we end up with this. Very cool. Now, we can dot both sides by E2, and it'll become clear why we do this in a minute, but if we dot both sides by E2, we'll end up with dE1 dt dotted with E2, and then a vector dotted with itself is 1, so E2 dotted with E2, you'll just end up with omega 3. We're going to do the exact same thing, okay? We're doing the exact same thing, but we're looking in the E2, E3 plane. So say we're rotating about E1, the E1 direction. Well, what is our parallel now? Our parallel is now E2. Parallel is E2. Parallel is E2. What is our perpendicular in this case? Our perpendicular is E3. Perpendicular is E3. And we're rotating by an angular velocity about E1. So omega 1. It doesn't get much more complicated than that, right? We're just applying this result we just spent all that time deriving. Again, this will become clear why we're doing this in a second, but we're going to dot both sides by E3. So we dot this side by E3, we end up with dE2 dt dotted with E3 is equal to E3 dotted with E3 is 1, so we just end up with omega 1. Finally, we'll look at the E1, E3 plane. And again, it's the exact same thing. This here is our parallel. This here is our perpendicular. Here's our perpendicular. And we're rotating about the E2 direction this time. So our angular velocity in the 2 direction. And again, it's about to become, I'm about to do the big reveal, but we dot both sides by E1, and we end up with E3 dotted with E1. E1 dotted with E1 is equal to 1, so we just end up with omega 2 on the right side. Now recall the dot product rule. E1, E2, E3, that's an orthonormal unit basis. Okay? So E1 dotted with E2, those are perpendicular to each other, so it's going to be equal to 0. E1 dotted with E2 is equal to 0. Taking the derivative of both sides using the product rule, we're taking the derivative of this, so we do the product rule. derivative of the first times the second plus the first times the derivative of the second equals 0. Derivative of 0 is 0. What is this term? Oh my god, we did it! Okay, dE1 dt dotted with E2. dE1, where did we do that? Where did we do that? dE1, E2, right here. That's equal to omega 3. Oh my god, omega 3. Okay, so this term's omega 3, which is equal to, all I'm doing is moving this over to the other side of the equal sign. That's equal to negative E1 dotted with dE2 over dt. Okay, so that's equal to omega 3, right? That's what we just said here. Similarly, if we do E2 dotted with E3, before we did E1 dotted with E2, now we're going to the next case. E2 dotted with E3 is equal to 0, also due to orthogonality. They're perpendicular to each other. Do the product rule. Derivative of the first times the second plus the first times the derivative of the second. And we end up with this right here. dE2 dt dotted with E3. dE2 that looks familiar. That looks familiar. That's omega 1. That's omega 1. So, again, I move this over to the other side. So, negative E2 dotted with dE3 dt, that's equal to omega 1. Let's keep going. Last one. E3, we're almost there. The payoff is going to be so good. E3 dotted with E1. Also, they're orthogonal to each other. It's equal to 0. Product rule. And we end up with, this term. This looks really familiar too. dE3 dt dotted with E1. dE3, oh my god, that's omega 2. Right? Was that the right one? Yeah, that's omega 2. Oh, cool. Okay, so we move this one to the other side. We end up with negative E3 dotted with dE1 dt. Sorry, there's a lot of words. This is equal to omega 2. Equal to omega 2. Isn't that awesome? Okay, so in the most general form, we can write that the change in the E1 direction is equal to something in the E1, something in the E2, and something in the E3. Okay, so recall that if you watch that 3 blue, 1 brown video, a dot product is a projection. A dot product is a projection. So we can find the E2 component of dE1 dt by dotting it with E2, which we already found. We already found what this was. This was omega 3. Okay? Similarly, we can find the E3 component. Now we can find the E3 component of this by doing the same thing. We just project it onto the E3 direction. Well, what's the change in the E3 direction? What is this? Well, we already found it. It's negative omega 2. It's negative omega 2. Where is that? Let me just show you this. dE1 E3. dE1 E3. Right here. That's equal to, if we bring the negative over, that's equal to negative omega 2. That's equal to negative omega 2, which is what we have here. Now, what about the last term? All right. So, recall that E1 is a unit vector with a fixed length. So, it experiences no change in the E1 direction. The E1 component should be 0, right? Because it's not changing length. But let's prove it just to show it. E1 projected into the E1 direction. We do the product rule. And we'll end up with 2 dE1 dt dotted with E1 equals 0. And we'll end up with the projection, the dot product in the E1 direction. That's 0. Okay? So we just proved that this dot product, which we did for all the others, is equal to 0. So now, if we go through the exact same exercise, and I'll leave that for you to do on your own. Don't you hate when people say that? I'll leave it for you to do on your own, but it really is the exact same thing. For the dE2 and the dE3, we'll end up with this. Right? We did this one together. I'm leaving it to you to go and prove these two to yourself. But this is what you're going to end up with. Now, if we let omega be, this is our angular velocity. Just let it be a general omega 1 in the E1 direction, omega 2 in the E2 direction, omega 3 in the E3 direction. We don't know what it is, we're just keeping it general. Then we can see that the rate of change of any of the unit basis vectors is equal to the angular velocity, this angular velocity, crossed with EI. Crossed with EI. Huh. Is it really? Well, yeah. So let's try it out. Let's try and find the rate of change of E1, the E1 basis. Well, what do? We take omega crossed with E1. So the rate of change of the E1 unit basis vector will be omega, the angular velocity vector, crossed with E1. Here's the angular velocity vector. We're crossing it with E1. And what do we get? We get E1 crossed with E1. That's 0. We get omega 2 E2 crossed with E1. What is that? That's equal to negative E2 crossed with E1 is negative E3, so we end up with negative omega 2 E3. And then E3 crossed with E1, that will give you E2, so we end up with omega 3 E2. And let's see if that's what we had. We have omega 3 E2, omega 3 E2, 0 E1, and the last one was negative omega 2 E3. Negative omega 2 E3. And you can do that for the other two, and you'll see that it works. So if you skip the entire derivation video, this is what you want to know. The rate of change of a unit basis vector, a unit vector, is equal to the angular velocity vector crossed with the vector itself, the unit vector itself. All right, so that's it. We'll do some examples next time. So see you next video.